tell us about polynomials and random permutations?
So thank you very much for the introduction and for giving me an opportunity to talk at this very nice workshop. So I'm going to speak about joint work with Charles Bordenave. Okay, so that's the archive reference. We can take a look at details. So basically, what we are interested in is to study the joint behavior of random permutations. So So I will denote these permutations by S1 down to Sk, and so they belong to the symmetric group on n elements, which in turn I'm seeing as permutation matrices. So this is n by n matrices, and well, very soon you will see that of course this is I don't need complex principle to embed the permutation matrices, but I will want to allow me to take some complex valued linear combinations. So I view everything as living in this matrix algebra, and what I assume is that all these matrices are random, independent, identically distributed, and they are distributed according to the Haar measure on the symmetric groups, on the uniform measure. So here it just means that the probability that a given permutation takes some value is 1 over n factorial. Since I will be interested in a large n behavior, I will put this here. So I will always assume these matrices to be this. So what I see as random matrices to be independent. I could assume that so if n is even, so if n is 2n prime, I can assume, I may assume that part of the matrices are random matchings. So actually, just to keep it simple, I will take random permutations, but we can make some modifications on the model, and it will not affect the results which I want to present today. So, what do I mean by the joint behavior? Typically, what it means is that if I take P, a polynomial in non-commuting entries in the free group on k elements. So this is, maybe it's not a standard notation. This is the free group on k elements. So this is generated by, let's say, G1, Gk, where there is no relations except Gij inverse is identity. So let's take an example. Let's say I would like to study, maybe just for the sake of of simplicity, I will assume that it's a self-adjoint polynomial in the sense where the adjoint of GI is its inverse. So let's say, for example, I would like to study P is G1, G2 plus G2 inverse, G1 inverse plus whatever, plus G3 plus G3 inverse. What is G3, G1 plus G1 inverse, G3 inverse, or something else. I could put some coefficients or whatever. So some kind of, linear combination of words in the free group, and out of this, I can create a random matrix, which is just I replace GIs by my random permutations. Okay. So I suppose one possible motivation for looking at this is we could think that this, for example, here becomes in this specific example, which is extremely specific, it becomes the incidence matrix of a graph. So you could think of it as this as a random graph on n vertices, and try to see what we can say about this kind of random graphs. So specifically, we are interested in the spectrum. So behavior. So what I mean by joint behavior here is behavior of the spectrum of Pn as n goes to infinity. So in my problem, P is given, and I would like to see what happens. Let me make one more remark before I continue to clarify to which extent I want to study the problem. Here, what I'm doing is I'm taking complex valued coefficients, a linear combination of words in the free group, of elements in the free group, with complex coefficients. I could allow myself actually to take a linear combination with matrix coefficients. So, for example, I could have something like this. I could have something like Q, which will be, again, I don't know, it could be some, if L equals 2, for example, I could have something like this. I could have G1 plus G1 inverse, and then G2 plus G2 inverse, and then, I don't know, G1, G3, G3 inverse, G1 inverse, whatever, something like this. And again, I can think of this if I want. So at least if the coefficients are natural numbers, I can think of it as again as a random graph. But I'm going to make no specific assumption on the coefficients. So what is the behavior in this generative of the spectrum as n goes to infinity? It is known, it follows from free probability, and I would like first to start explaining this here. Free probability implies that the spectrum of Pn converges towards something deterministic. So let me deterministic in expectation as n goes to infinity. So to be more precise, what I would have to do here is I would have to, so since I took just for the purpose of simplifying things. Actually, I don't need to do that, but it will just make my life slightly easier. If I take a self-adjoint P here, it means that this guy will be self-adjoint as well. So I could describe the eigenvalues as being, I could arrange the real eigenvalues in a decreasing order. So I could call them something like this: lambda 1 n bigger than lambda n n. So here I put an n, but of course if I had allowed myself here to take matrix coefficients, this could have been ln here as well. Okay. And then I look at the so-called eigenvalue counting measure. So eigenvalue counting measure, which is 1 over, so which I will call mu of Pn, which is 1 over n sum for I of the Dirac mass at lambda in. So here again, put an NL if you want, if I put matrix coefficients. So Pn is random. So this is a random sequence of n numbers, a random non-increasing sequence of n numbers. So this is a random probability measure. And the meaning of this random probability measure is if I take an interval, let's say, it means how many percent of eigenvalues do I have in this interval. And what free probability tells us is that there exists a measure, a probability measure mu, a real valued probability measure, such that mu Pn converges. So maybe I will put the expectation of mu Pn. So the average converges to mu P. So again, specifically, slightly more specifically, it means that if I check it against test functions, so integral of f of x d mu Pn of x, this converges towards integral f of x d mu of x. And here, so this is a random real or complex valued variable, so I would take the expectation, let's say, and this converges as n goes to infinity to this for some appropriate choice of test functions. So typically we could take a bounded or compactly supported continuous functions. It turns out that it is enough by some elementary approximation properties to take polynomials. Even real valued polynomials would be enough. So let me explain a little bit how this works. So it's enough to prove it. To prove it for monomials. For monomials, and in this case, what one has is that what one just has to observe is that the expectation of integral of x to the p d mu Pn x. This is the expectation of the normalized trace of my random polynomial to the power p. which itself is a...
Darker marker.
Yes, let me... Thank you. So, P is an element of this algebra. So is P to the power P. So again, by linearity, it's enough to prove it. So it's enough. The one which works. Just ruling them out one after the other. Okay, thanks. So if I, are you sure? Oh, maybe I'm not holding it properly. So if I expand, so it's enough to prove it when P is a word. So not a combination of words, but just a word. And here actually we have an old, quite old result from I think from Nika from Andrew Nika of the 90s, which says that so if so I will replace P by W for a word if I take just a word in the free group and I replace, like before, each generator by the random permutation. Let's take a non-trivial word and trace of the random permutation which is obtained by replacing each generator by the permutation has expectation which goes to 0 as n goes to infinity. What it says basically is that that's the, if you want, the expected percentage of fixed points. So it's quite a nice result somehow. I mean, not very difficult to prove. That's as soon as I take a word which is non-trivial, if I look at the permutation which I obtain from there, it will have only few fixed points. The trace is the number of fixed points. And by the way, this is in free probability we have a fancy word for this. We say this is asymptotically free. So we said S1 and Skn are asymptotically. So now you know what free probability is. That's all what you need to know about free probability. Basically that's enough to prove this. So it's, in a sense, it's almost disappointing that we just need this to conclude that we have the existence of such a probability measure. But that's how it is. And from this now, two directions that we can take. The first one is what does this measure look like? So I'm not going to possible developments. So what does mu p look like? And another one, which is the one about which I want to speak today, is do we have outliers? So let me elaborate a little bit though on the first point first. So somehow this result has been known in the 90s, but there is a little bit of frustration due to this result, because let's say if you give me a measure mu, if you give me a polynomial create? Can I compute the measure mu p? Not really. Actually, it's quite difficult to compute the measure. So nowadays there is actually if instead of taking random permutations we had taken some more complicated matrix models, then there was a tool which is called the Voiculescu's R transform to make some computation in some cases, but even that was not systematic enough in a sense. And nowadays there are very general algorithms for computing mu p, which have been developed by many people, including Belinsky, Speicher, many others. So in principle, nowadays, if you give me, or if you give these guys your favorite polynomial, they can put it in a computer and tell you what mu p will look like. And there are many other things which are known, many theoretical properties which are known about mu p. For example, it is known that except if p is trivial, the measure mu p has no atom, for example. Or it's known that in the case L equals 1, the spectrum is connected. Or lots of properties which are quite nice, whose proof in general requires either some smart arguments with skew fields or with C-star algebra and all this. But anyway, quite a few is known about this. And what I want to discuss is the other part, which is do we have outliers? So here, what do I mean? What do I mean? The thing that we know for sure is that mu p has compact support. Okay. Everything is bounded, so we're adding bounded things. But the dumb bound that we could set on the support, like on the right, it's at most the sum of absolute values of all coefficients appearing in the sum or whatever, are very gross bounds which are not the right bounds. And so let me draw a limiting distribution. What this result tells us is that, so this is, let's say, this is my limiting distribution. What this result tells me is that if I look, let's say, a compact set which has no intersection with the support of the measure, what this tells me is that I have little o of n eigenvalues there. That's all what asymptotic freeness tells me. As soon as I don't have a macroscopic amount of eigenvalues, I don't see them, and then the limiting support is 0. But so any eigenvalues which would be here would be called, we would call it an outlier. Okay, so any eigenvalue which is epsilon away from the limiting support, epsilon away from the limiting support, so of mu p. And well, we can have outliers. It's possible to have outliers. So outliers can happen, of course. And the most canonical, perhaps, example is if I take, so I will take a p which is not self-adjoint. That's all right. If I take p, which is, let me call it z for this on this occasion. So zn is s1n plus skn, just the sum of these guys. Of course, this one has an eigenvalue which is k, right? So this is the Perron-Frobenius eigenvalue. But if we look at the limiting distribution of the singular values here, I mean, we can handle the singular values in the same way by taking it with its times its conjugate. The limiting distribution has a spectrum which ends at 2 root k minus 1. So as soon as k is at least 3, this one should be considered as an outlier. So we have an obvious outlier. So this one is obvious. And so the question becomes: do we have non-obvious outliers? Do we have non-obvious? And basically, our theorem says that we don't have non-obvious outliers. So let me just state the theorem. The theorem which I want to present today, if I make a shorthand statement of the theorem, is so there are no non-obvious outliers. Probability as n goes to infinity. So maybe I should, well, I think it's already possible to make a rigorous statement out of this, but let me precise a little bit though. What we do is we take a self-adjoint element here. Oh yeah, and by the way, so this is true here. I should mention this is true for any P which belongs to the matrices, the matrix valued coefficients in the free group. So okay. Then so what you do is to remove the obvious part. We are going to view SIN not anymore as acting on C to the n, but on the orthogonal of the pair of Frobenius. So they are acting as endomorphisms of the orthogonal of the pair of Frobenius. That notation. Okay. You can think of it as an n by 1 times n by 1 matrix. Okay. So I will call them S tilde I n. Okay, and then what I do is I call so P n I already defined it. So I will define P tilde n, which is a matrix in Mn minus 1 of C, which is obtained by replacing not anymore by Si but by S tilde I, Gi by S tilde In. And then what we have is what we want, namely that for this polynomial, the probability that the operator norm of P tilde n bigger, so for any epsilon bigger 0, the ptr and operator norm is bigger than the operator norm of p plus epsilon goes to 0 as n goes to infinity. Here, well, that's well defined. What I mean here is that I view P as an element of the bounded operators of L2 of the free group on K generator. If you prefer to keep it slightly simpler, to each P I had this probability measure mu P, which I could compute, and this is just the spectral radius of the probability. This is the max of Z for Z in the support of mu. So that's the statement. And let me.
So may I ask something? So it seems to me that these two statements are not technically equivalent. I mean, the first statement looks like as if you say that a random irregular graph is Ramanujan with high probability. The other one is more like the theorem of that the random irregular has spectra radius 2 times square root d minus 1 plus.
Yes, I agree with your statement. So, yeah, I agree with that's a very good question. The statement here just says something about what happens on the right basically. And for example, let's assume, which, like I said, is not impossible, is L is bigger than 1, that you have a spectrum which is not connected. Then what I claim here is that even in the middle there is no outliers. So in a sense, I'm claiming more here than there. But it turns out that I have actually a quantifier on the polynomial. This is true for all polynomials. So then there are some tools you can somehow you can fold your polynomial, like square it, and then well, it turns out that these two questions actually these two statements are equivalent, but it's not completely obvious, but this happens to be the case. Okay, so well, what I should perhaps do now is, in the last 10 minutes, right? Explain a little bit how, well, a little bit of history and outline of the proof. Well, first of all, of course, and that was, I think, related to your question, the particular case of I suppose of maybe I suppose of Zn plus Zn. So this is like a random undirected Schreier graph or something like this. Is of course of particular interest, because what this tells is that this is with high probability, this is close to Ramanujan. So this is with high probability, this is close to Ramanujan, and there exists proofs of this result. I mean, I think papers of Friedman or Bordenave who handle this. So in a case we can So this is just one particular polynomial, and we can view this as a particular case of our theorem. We can also, even though I'm not going to comment too much on this, we can also view our theorem as handling much more graphs than just this specific example of graphs. But so somehow this was Bordenav's Charles' point of view, and my point of view was slightly different. Probably, I think ultimately it was less interesting, but somehow this problem was also quite important in operator algebra. So in operator algebra, we are interested in finite dimensional approximation property of some von Neumann algebras or C-star algebras. So there are lots of complicated objects, and you would like to know if they can be approximated by finite, in some sense, by finite matrices or so. So perhaps you heard of the famous cone embedding problem, which is not completely related to this, but which was somehow inspiration to some extent. And so somehow the problem of approximating what we call the free group C-star algebra or free group von Neumann algebra led to some previous results. Which were that the same theorem as here, holds true if one replaces random permutations SIN by random Haar unitaries. So this is random Haar unitaries. So this becomes really actual random matrix theory. We take the unitary group, which has a unique left and right invariant probability measure, the Haar measure, and instead of taking random permutation, we take the Haar measure, and then the result holds true. And that was actually something which had been open for quite a while, in maybe for 10 or 15 years, at least in operator algebras. So there was a very big first step, which was achieved by Hagerup and Torbjørnsen. Around 15 years ago. They proved it for something we call GUE, Gaussian unitary ensembles. And then together with Camille Mal, we proved it for random unitaries. So in a sense, my point of view at least, was, well, let's replace this probability measure by another one and see what happens. And was not aware at that time of the odds of what was at stake on the graph theoretical point of view. But it turns out that the proof here is actually easier than the proof there, because this is a continuous measure on the Lie group, and we have lots of very powerful analytic tools. Like we have things like Schwinger-Dyson equations and all this. So lots of things which don't work if you have a discrete measure. So any tools which were available here were not available there. And we needed some, so somehow even though it at first sight looked like a direct extension, lots of new tools were needed. And I will just finish by mentioning two ingredients of the proof. So two ingredients of the proof. One which I think is very well known by people in graph theory, and one which is very well known in operator algebra. So I will start with the one in operator algebra, which is called the linearization trick. So the linearization trick. And the statement is as follows. So the way I could state the linearization trick is that it is enough to prove the theorem, the main theorem, for P in ML of Fk of degree 1. Of degree 1 in the world. So namely, something like this. Maybe I could write like this. A minus K tens S, whatever, G minus K plus A0 tens G0 plus AK tens GK, where I take the convention that G minus K, G minus I is GI inverse. And that's all. So if I can handle this, that's enough. And this is quite surprising, at least at first sight. I think it's quite surprising because here we have a statement about all polynomials. So I have a statement about degree 2, degree whatever polynomial. And I'm telling you that it's enough just to look at constant polynomials. It's enough to look at constant polynomials, but of course there is a price to pay for this. It has to be true for any matrix, coefficient here. So I have a quantifier on for all L, and for all A minus K, AK. Basically, that's the linearization trick. And once we have this, we're already in better shape. We're already in better shape in the sense that anyway, even Hagov used this trick. So somehow this trick had been known forever in operator algebra. It was introduced by Pizier for the study of operator spaces and all this in the 70s or so. But it is, I think, Hagov who realized that it can really help to solve some important problems which are not only directly related to operator algebras. And then it got really publicized quite a lot in random matrix theory. So that's the first trick. And the second one is, so since we may not use analytic techniques. By analytic techniques, basically, I mean this plus some complex analysis related to Stieltjes transform and all that. Since we may not do this, because we don't have some nice change of variable formulas and all that, we have to use moment techniques. And moment techniques don't work directly. This is handling this with signs or matrix value coefficient or this is just too complicated. But that's not a surprise. I understand that's for these random graphs, similar problems already occurred. And actually, one thing which works is to use some non-backtracking operators. So we have to do some non-backtracking operators. So non-backtracking operators, again, as far as I understand, were studied quite systematically if you had one coefficient all around here, or at least maybe complex, whatever, scalar valued coefficients. So what we just, so to say, had to do is to check which kind of non-backtracking theory we get if we replace scalar coefficients by matrix valued coefficients, and it turns out that actually the theory extends rather naturally, and then we are everything boils down, so to say, to computing moments not of this, but of a non-backtracking, of an operator-valued non-backtracking matrix, which is associated to this problem, which, even though to me it looks more complicated, becomes tractable in terms of computations. I'm over time, so I'll stop.
So does it allow to reprove Friedman theorem in an easier way?
Yeah, I mean, so Charles Bordenave actually wrote a paper where he reproves a Friedman theorem, and somehow I would say that his paper, in a sense, is a strict subset of our paper. So these are really techniques which he started developing in his paper, which we extended to the operator-valued context.
So this relationship between the non-backtracking and the actual matrix is something like the Harabas identity?
Yes, there is this quadratic relation between.
It's a similar form.
Yeah.
Yeah. So, but the eigenvalues of the non-backtracking matrix, because it's not normal, are probably not nice, right?
Yeah. Yeah. So right. So in the I was a little bit quick when I did all this. Actually, the linearization trick has many versions. So there is a unitary version, there is a general version, there is a self-adjoint version. So somehow the self-adjoint version was quite useful in the beginning. We are also using the self-adjoint version. So we would ask this guy to be the adjoint of this guy or something like that. But indeed, the non-backtracking matrix will not be normal, and then we have actually to look at the spectral radius.
So you only use the spectral radius?
Yeah.
Okay, nice. We'll meet again at 4:15 for discussion.